All right. What's up, everyone? Welcome to week 116 of building my own operating system. So, got a couple cool things lined up for today. I got basically a big mystery lined up. And just to kind of give a bit of an update, so I'll actually be traveling for a couple weeks, so I've pre-recorded a few streams. The next 3 will be pre-recorded, and I did that yesterday. And so basically what we're doing today is not contiguous with what was streamed last week. There's a bunch of hidden progress that you haven't seen yet, in case you've been following along. And then that hidden progress will be released in the coming weeks as pre-recorded streams. So what we're working on today is a little bit of a new topic that has never been seen before on stream. What's up, Sensei? Also, okay. I was wondering if my OBS like chat widget was like weird in this area, but no, it's just the screenshot over here. Nice. Got the crew popping up. What's up, MG Tech? Hi. All right, I'm just making sure things are looking good on the stream end. So I think got a couple people in the chat. What's up? What's up, everyone? What's up, Vibov? What's up, Saketh? Yo, hello. What's up, Rada? Finally, no LLMs. Thank God. Love these streams. Finally, some signal from the noise. Thank you. I mean, I gotta say, I gotta be very transparent. I do use LLMs occasionally, and so I don't want to claim something that I'm not doing, but I can guarantee you that I'm trying to not vibe code the OS. I'm not vibe coding it. I'm using AI selectively where it makes sense. That's the motto. What's up, Lynn Coding? Why you choose C++, not Rust? I got you. Very, very commonly asked question. And I'll see if the chat bot is even active today. That is taking a long time to answer. Basically, I just don't know Rust. It's very simple. I simply do not know the Rust programming language. That's crazy. It seems like the chatbot is really absent from the stream today. It's not answering anything. Modula 2 OS when? Oh, crazy. Modula 2. That's a language, right? That's like... I remember hearing about Bjarne Strustrup talking about being influenced by Modula 2. So maybe someday, maybe we gotta whip out the Modula 2. Okay. So today, I got a mystery for you all. We're gonna debug something kind of wild that happened when I was working on my OS yesterday. Before we get into it, I'll just see if there's anything else. Okay, chatbot is completely absent. So that's just how it's gonna go. All right, so we're out here, week 116. I got a little warm-up exercise for myself, and then we'll get into the meat of the stream today. So I've been doing a bunch of work off stream, which is going to be posted in the coming weeks. I need to be away. I'm not able to do live streams because I'll be traveling, and so I've pre-recorded a bunch of content to go out. I will try to join the pre-recorded launches, but basically I've been working on smart pointers, and I'll tell you about that. I'm pretty excited about the smart pointer support that I got working. And so that's what a couple of these streams are about. First one, I was hand rolling a smart pointer. Second one, I was trying to not hand roll a smart pointer, and I was trying to actually use, for example, unique pointer from the standard library. And I had some success with that, and I'll show you that in 1 second. So adding my first smart pointers to the OS, and then sorry, 1 second. Okay, cool. And then I was working on this whole idea of pre-initializing the guard pages, or pre-unmapping the guard pages, and that's a little bit of a specific thing, and that's related, I think, to this debug 4,000 tasks thing, which I'm going to get into today's stream. So that's the idea. So King Knight, it's crazy. I think the bot is literally not working today, and that's just unfortunate. So basically, yeah. These are chat commands that usually the bot answers. Yeah, back to the Rust thing. I just don't know Rust, and I know C++ very well. And now is not really a good time for me to learn Rust while I'm also learning this other hard thing. So, yeah. And Lynn Coding's asking, what is the build tool you're using CMake? Well, first of all, welcome to the stream. Thank you for joining if it's your first time. Really appreciate you popping in. And yes, I'm using CMake for my build system. CMake with mate files. Bot needs time. Bot's on vacation. Bot's out to lunch. Bot's I don't know where the bot is. All right, let's talk smart pointers. So I'm actually really excited about this. So here's the struct task that represents a kernel task, kernel thread, kind of kernel stream of execution. And I wonder if the Git will tell the story pretty well. Init smart pointer. So formerly the task was storing a raw pointer to a task stack, and it was the responsibility of the scheduler to allocate a task stack and then also to free it. And that's what we're seeing here. The scheduler is allocating a task stack and passing that into the constructor of the task. And then on the other end, it was needing to destroy or free or release that task stack back to the pool. And this is manual, so it's manually allocating, manually destroying. And I need to remember to do this in my code. And this is a classic use case for a smart pointer. And so this is a classic use case for C++ smart pointers. So what I did was I hand rolled this kind of basic, kind of bad smart pointer. It doesn't really have any advanced features of smart pointers. It's the bare minimum, but it's just this type that calls destroy, that destroy thing when the thing goes out of scope, which is the fundamental recipe for a smart pointer. And that allows us to replace that raw pointer with this smart pointer. It's called stack unique pointer for some reason here. That's not the final name, but the benefit of this is that now I don't need to write code to remember to deallocate the the stack. All I need to do is make sure that the destructor for the the task gets called. And if I do that, then C++ will make sure that the task will automatically get destroyed. The way the destructor gets called is as part of the linked list. And so when I call tasks.erase and pass it this task to be cleaned up, the linked list is going to run the destructor for the task that's being erased. And so that's nice. This is just classic smart pointer, nothing really too fancy about it. I hand rolled it just to prove the concept in a very basic way. And then what I was trying to do after that was not hand roll it. And this is the final form that I've arrived on. I'm actually able to use std unique pointer from the C++ standard library for this. And std unique pointer is flexible enough where it can be customized with a deleter, which is exactly what I need. And so I have my custom deleter, and then I have a little wrapper function that makes it a little bit easier for clients to construct this thing. And now we're using the task stack unique pointer everywhere, which is really cool. And so now the task stores a task stack unique pointer, and it is the scheduler that's responsible for constructing one right here when we create a new task. Also, when we construct the idle task, which is a task, we're making this task stack unique pointer. And then lastly, I think there's one other place. Maybe not, actually. Maybe. I thought there was one more. Is it in the... Okay, maybe I was imagining it. So that's the idea. That's the smart pointer. Pretty happy with that. And then, yeah, so that's going pretty well. Let's just check in. I'll just see how many people are in the chat. I literally can't. Oh, 18. Shout out to the 18 people in the chat right now. Okay. You know, I could have sworn there was some other. Okay, I see, yeah. This thing went away because it was dead code, it was unused. Yo, what is up, Digitalized? Digitalized in the house. Nice to see you, man. What's up, Jason3427? Gotta ask you why you build your own OS? Absolutely. It's fun. It's just super fun, and I want to learn how OSs work. And I personally have this vision to write an OS in modern C++, like a small, minimal, clean OS in modern C++. And I want to test my own personal abilities and see what I'm capable of. So that's pretty much why. Word. So anyway, that's super cool. We got some smart pointer action going on here. I'm very happy with that. Let me clean up some of these tabs. So now let me do the warm-up exercise. So the warm-up exercise for today, don't assert for the idle task pointer. What does this mean? So it's pretty much this comment. One thing that is not very clean about the way I've implemented it right now is, we'll just read the comment. Technically, this will assert when the idle task is destroyed. We could use an if instead, but that introduces a branch on every free. Alternatively, the idle task could come from a pool of 1. So here's the idea. We have this task stack deleter, which is part of the smart pointer that manages the task stacks. And yeah, normally this is create task is the main place we're dealing with this. We allocate a stack from the pool, and then construct a smart pointer and pass it to the task, which is going to hold that, and that's going to make sure we always release the task. We have to pass in a pointer or like a reference to the task pool, because we're storing it here, and then we are releasing the task stack from this particular pool. And the thing that's tricky about this is that almost all tasks on the system have their stack allocated from the pool of task stacks, but there is one exception, which is the idle task. The idle task is a special kind of task. It does not live in the normal container of tasks. It is allocated separately from that container. The reason it's allocated separately is because it allows the scheduler policies to be nicely isolated from the concept of the idle task. And so the scheduler policy doesn't need to know that there's a special task within the task list that's the idle task. From the perspective of the scheduler policy, anything within the task list is pretty much equivalently available to be scheduled, and there's no special logic or reasoning around that, which makes it very clean, where the policy can simply return a null pointer if it could not find a task. And in that case, we use this separately allocated idle task. Otherwise, if the idle task was in that list, the scheduler policy would need particular logic to handle that. So that's why I've designed it this way. The problem is that the idle task also needs a stack, and its stack is also statically allocated. And that's actually something to think about. So I guess there's a couple options here. So option is to allocate the task stack separately. I could also consider something different. I could also consider allocate task stack inside the normal pool, separately statically inside the normal pool. And then third option, third alternative, we could have a pool of 1, size 1, just for the idle task stack. But before I get into that, I'll explain the actual problem though, but I'll check the chat. How do you know the steps for building an OS? Asked by Jason. I would not say I completely know. I would say I have a rough idea of the next immediate things, but it's not exactly like I have like a really just like long, very detailed roadmap or something like this. But and a lot of my general understanding comes from this MIT course, which I live streamed myself doing about a year ago. And it's very possible that that chat command is just totally busted because the bot did not show up today for some reason. So maybe I can super quickly try to fix that. But basically I took this OS course and that gives me a lot of my base understanding. What's up, Felipe? What motivated you to want to create your own OS? I sort of answered this, but yeah, I am just super curious to learn about OSs. Building one is the best way to learn. And I have this personal vision of doing it in C++. Somehow my YouTube cloud bot became inactive. I just reactivated it. Let's try. Again. I don't know if it'll reactivate in the middle of the stream. Okay. Okay, there we go. Say hello to chatbot, everyone. So back to this. The real problem though is, okay, the problem with the current implementation, and so the fact that currently the idle task has a task stack that is statically allocated. It's not in a pool. Therefore, it doesn't need to be released. There's nothing to call release on. But the problem is that the task structure sort of mandates that you have this unique pointer to a task stack. It stores a unique pointer, it receives one as an argument to the constructor. And so to work around that, I allowed clients to pass null pointer for the pool. And so you typically pass a pool into this thing, and that's the pool that the task stack will be freed from over here. And I don't want, there's no pool to free from. And so for that reason, I've made it possible to pass a null pointer into this thing, and it stores here. And then the question is, what do I do though? So currently I have it asserting actually, because the thinking was that the idle task should never really be deallocated. But that's sort of true. The idle task remains available for the entire lifetime of the runtime of the OS. But the part that I wasn't really thinking about is shutting down and tearing the OS down actually. And so when I haven't really worked out how shutdown is going to work, but if I wanted to be really a well-behaved citizen of like C++ and everything, I would make sure my scheduler class can be destroyed, and that means the idle task destructor is going to run, which is going to try to basically deallocate that. It's going to run the destructor of the smart pointer, which is going to hit this assert here. So that's just problematic. It's not good form to have an object that asserts on destruction. It is better form to make sure your objects can gracefully, obviously get constructed, but then gracefully destruct themselves. And so that's what we're talking about here. And so the question is, how do we make it more graceful? What's up, Julius? Why are you writing a kernel in C++? When you can write a kernel, you must be writing with C or maybe Rust. Popular question today. The simple answer, I'm pretty good at C++ and I just don't know Rust at all. So let's get coding. And so the idea here is we're no longer going to have an assert here, and we're going to find some way to have this idle task stack be freeable. And I guess one option is I could just basically do numtask plus 1 here weirdly, which is like kind of odd, meaning there's space for k num tasks for their stacks plus 1 extra one for the idle task, but somehow I just don't really love that. And what I'm leaning towards is idle task stack pool. And now what we're going to do is idle task. Now over here, instead of passing a pointer to this class member, I am going to call the create thing. I'm going to allocate, allocate and I'm going to pass in the midle task stack pool, and this is going to require me to. Now we can go back to a nicer version of this, where it takes a. This is now a reference, so we've gotten rid of the pointer semantics, which is really nice. And then lastly, we can come over here and make this a reference, get rid of this thing. And then we can get rid of this assert and then make this a dot. And I think that's sort of how this is going to look. It's always a really, really good feeling for me when I can convert something that was a pointer argument or anything into a reference, because that means I no longer need to worry about the case of if the thing is a null pointer. I can just be guaranteed that this will always be pointing to a valid object, like 99% of the time at least, because C++. So that's sort of how this is looking so far. And I get to delete this comment that's like, when it was a pointer, I needed to explain what it means if this thing is null. Like if null pointer asserts that something is deleted through this is never used for long-lived task stacks that are never free. Like once this is a reference, I can just get rid of this entire comment. There's just like so much less to explain. I can even get rid of this comment probably. It's just so much nicer. So that's sort of, and it wasn't a lot of code. I think I have some other call sites to clean up. So right here, here's the call site. I need to no longer pass a pointer. I just pass a reference. Digitalize with the hot take. Ever since I started using C++, I like it a lot. Well, I know you guys a lot of hate online, which is maybe why you see so much hate of it on stream. Yeah, man. Yeah, I think C++ is kind of a misunderstood language. I think it deserves a lot of the hate that it gets, to be honest, but I also think it is very misunderstood. I think a lot of people that criticize C++ don't actually have experience working with it in its sort of like optimal form, because there is a way you can write C++ that is even beautiful, I would say. And for me, that's what I'm trying to do in my code. I'm trying to make it, compact, not have a lot of mutation, avoid like pointer semantics and like the arrow operator all over the place, use references. And I think, yeah, it's possible to write nice looking code in C++. There's still reasons to not use C++, but it's not always this garbage fire that everyone's talking about all the time. So I think it's good. I think it's good to know C++. Yeah. What's up, Higgs boson? Damn, we got the Higgs boson in the chat. RAII, absolutely. And I'm using that. I'm like actually starting to use RAII in my kernel. Literally with this stuff that you're all seeing right now, this is the first use of RAII pretty much in my kernel for this unique pointer. And I mean, I can actually get rid of this. So this is actually all that's needed. This log isn't really needed. And so, this thing becomes really compact if we whittle it down to the minimal form. For the moment, I'm going to keep the log because it's useful for debugging and verifying that things are working. But let's check it out. So we should be compiling. Oh. Okay, what did I miss? Oh, I did not. Ah, okay, okay, so this is a good learning opportunity. And this is also a good reason to hate on C++. I just coded a very subtle bug. Okay, I mean, yeah. This is exactly what I'm talking about, where there are valid reasons to hate on C++, and I literally just did one of them. The very subtle bug that I just did, and I've also seen it in production, it's really easy to miss, is that with C++, you need to be very, very careful with how you do your construction of objects. And you need to be very careful to not use an object before it has been constructed. And the order of construction is determined by the order things are declared in a struct or class. And then you'll notice that my idle task is declared before the midletask stack pool. However, in the construction of my idle task, I am assuming that the midletask stack pool is valid for use, which is not a valid assumption, and is like undefined behavior. And I only realized this because my compiler warned me about it with this w uninitialized. So I think a really key caveat to my statement about C++ being like good is that you need to enable compiler warnings, aggressively enable a lot, or like, all of the compiler warnings you can. Here, what do I enable? These are my C flags. I think this is an incomplete list. I think I got this from like an AI or something like this, but I'm running with a pretty large set of warnings of various kinds. And I'm not quite sure where uninitialized comes from, but it's probably in one of these. So yeah, UB is really bad, the language. That I hard agree with, but also with C as well. Yeah, it's a good point. C also has UB. I would say just the complexity of the language of C++ makes it easier to run into UB than with C, I think. Anyway, quick 20 seconds, stand up and stretch. All right, so we got to fix that bug. And so, these things are this kind of thing is very, very subtle. I've seen really senior C++ developers make this mistake also. So this is really easy to do wrong. And sometimes you don't always catch it. So a easy way to fix this is to do it like this. While I'm at it, I can also just sort of reorder things a little bit like this. I'll just clean things up. So now you just need to make sure your ordering is correct. And so now task stack pool gets constructed before idle task. So, and we're back to compiling cleanly. Julius says, I'm working on my own project and writing my own kernel, but it will be a project suitable for scientific research. What do you think? I think that's awesome. I think if you're writing your own kernel, you are an awesome person. And I want to see it. I want to see the kernel, and I wish you all the best. You should post about it in my Discord. And because I know a lot of people would be interested in that there too. Yeah, if you're building a kernel, yeah, you're cool. Okay, so that's how we fix this basically. And so now Yeah, that was just the warm up basically. That was just like a little warm up, clean up kind of thing we can do now. So that's cool. Just gonna let's check out what the Git looks like. Okay, this. Okay, I have a bit of a messy situation. This is useful, but then not everything here is useful. So this is useful. That's not. This is all sort of relevant cleanup. This is okay. Cool. So this is our commit. It's just everything related to what I just did. Changing this thing to take a reference to a pool. Making sure we always have a pool that's backing any task stack that existed, and that's it. So cool. So clean up, use ref instead of pointer for pool. Okay. So the warm up of the day completed. My pen tool. Warm up of the day has been completed, which it means it's time to get into the real meaty topic for today. Debug the 4,000 tasks thing. What am I talking about? So, like I said, I've been doing a bunch of work off stream, which will be released in the next 3 weeks when I'm traveling and unable to do live streams. And what I'm going to be working on right now is the result of something I was doing in what will be week 119. But you get a preview right here. And so what I was doing is I was working on this topic, pre-initializing the guard pages, like unmapping them. This was something that formerly lived here. Formerly the task, when it got constructed, it always unmapped its guard page. But the problem with this is that it's like kind of wasteful. After enough time of the system running, you know, there's a fixed amount of guard pages and stack pages on the system in the way I've designed it so far. And so after just some point of enough tasks running, all of these stacks will be initialized at some point, and this is what the task stack looks like, and its guard page will have been unmapped. And so it just doesn't really make sense to just keep doing this unmap if at some point they're all unmapped anyway. So the idea is to make sure to the idea is to do this up front. So rather than doing it when a task gets created on boot up, like as part of the system boot up, what I want to do is I just want to go through all of the possible stacks on the system and just make sure that all the guard pages get unmapped, like just right up front. And then from that point on, the task doesn't need to do this because it can assume that its guard page is unmapped. And I thought I had something that I think that was like kind of working, but it is, I'll show you, it's not working. What is up, non-existent in the Twitch chat? Nice to see you. Honorary Twitch chatter today. Okay, I did something. Okay. So that wasn't it. I realized I forgot to increase the number of tasks on the system. But what I will show is I'll explain these lines. And so I have it, I think it seems to work for low numbers of tasks. And so as a reminder, This also might need to be inline, but I think that's not really relevant to what we're doing here. As a reminder, I made the pretty controversial and opinionated decision to have fixed numbers of like kernel objects for various things, and I have a fixed maximum number of tasks that can ever exist on the system, which is a opinionated way to do it, more in the style of embedded programming and real-time operating systems. And this is not in the style of desktop operating systems, to be clear, or even like server operating systems. But it's in the style of more embedded real-time OSs. And currently there's only 4. Well, I've been like bringing up all the infrastructure for task switching and scheduling, like all this stuff. I've kept it at an intentionally limited number of tasks just to keep things understandable. And obviously 4 is a pretty small number, and so eventually we want to crank that number up. And I was trying to do that, and that's what caused the issue. but in the current state of the code right now, it's still coded at 4. Digitalize saying, I believe that's what many RTOS do. I read that the micro C OS does that. Yeah, I mean, to be honest, I don't have like a tremendous amount of experience of RTOS programming. But yeah, this sounds about right to me. It's sort of just consistent with the way a lot of firmware is written, where you just make some trade-offs, and what you do is you just pick numbers for the maximum number of things, and as a trade-off, you get more determinism for the way the system operates. You can reason about the system statically better, like less things are deferred to runtime decisions. So, and as a trade-off, you lose a little bit of flexibility, like let's say, you know, I mean, with the hard maximum, the system's kind of brutal. You just cannot, if you need a 5th task, that's just sorry. Like, even if there is memory available on the system, if you need a 5th task, sorry, you just can't have one. Whereas the style of more desktop or server-oriented OSs, it's more flexible. It doesn't exactly know the workload that will be running on it, and so it moves more things to runtime, and it's a bit softer. And so it's like, okay, I don't have a fixed maximum, and so in case a certain workload has a low number of tasks but a lot of other like memory usage, I can accommodate that. But maybe there's another use case where there's a lot of tasks but very little usage of the other thing. We can also accommodate that, and so it's a bit more flexible at runtime. But then you lose some determinism and ability to reason about the behavior of the system when you do that. So anyway, that was just a bit of a diatribe. In my company, I build Windows driver APIs where operations go through structured system calls. You can't touch the kernel. Windows enforces strict boundaries, so I respect kernel developers so much. Me too. Yeah, I respect professional kernel developers a lot too. Yeah, I mean, I'm very much not a professional kernel developer, and I can see how complex this stuff gets. Julius asks, what type of kernel are you writing right now? Is it monolithic or hybrid? It's monolithic. Super monolithic for now. Just in the name of simplicity. So monolithic kernel. I don't have a user space. I'm not even that interested in having a user space. And so it's pretty much as monolithic as it gets right now. Which allows me, what I get from that is I by keeping it ultra monolithic, I simplify the system a lot. And it allows me to focus on core elements of the system like the scheduler. And I avoid a lot of complexity from like having a user space and stuff, which at this current point of time is mostly a distraction for me. So let me explain this thing. So here's how I've implemented unmap guard pages. The idea was on boot up of the kernel, we're just going to go ahead and just go through all the guard pages and just like unmap them. And it's a little bit more complex than it sounds, because it's not like we don't just have the guard pages in an array somewhere and we just like iterate over them and process them. The guard pages are stored in this thing called a pool, which is sort of like a very specific kind of memory allocator, which it's like a very specific memory allocator for exactly one type of thing that it can give out. And so it's this pool thing. And so you can't just like iterate over everything, because you need to like allocate from the pool. And what's up, Asans? Nice to see you. And so the idea is that in order to actually do this, what I need to do is like pretend these 4 things are the 4 slots in the pool. I need to actually go out and like allocate the first one, unmap it, and then I can't just like release it and then allocate again, because I'll get the same one again. So I need to be holding like references to all these things while I do this in order to ensure that I'm gonna get every one and I can exhaust the pool. But the problem is I need to keep track of these things as I pull them out of the pool so that I can later release them. And in order to keep track of this thing, I need some data structure to like do that. And I can use a static vector, which I have. I could even maybe use an array. The problem is that when the number of tasks gets really big, the amount of memory that this list of pointers is going to consume is also going to grow quite large. Let's say we have 4,000 tasks on the system. At 8 byte pointer, 8 bytes for each is like 32,000 bytes, almost 32 kilobytes of space just to store this list of all these pointers to things. And that is not an amount of space that is viable to store on the stack. And so that's why I was getting into my first kind of weird way of doing a dynamic memory allocation, where what I've done is I added a function to my physical memory allocator, which allows me to allocate a contiguous range of physical memory. And then once I have that, I can then use that to store a vector, this ETL static vector, into that memory, which is not on the stack. That's like the key point. I could try to just put this on the stack. I could try to make it a static variable so it's not on the stack. But the problem with that is that it's just incredibly wasteful, because this memory will just never be used again. So that's going to waste 32 kilobytes of memory for the lifetime of the system. And so that's why I'm going for this this way of doing dynamic memory allocation, which is a little bit interesting, because I'm dynamically allocating a region of memory so that I can allocate a static data structure into there, sort of. Then I can release it later. So basically, the main idea is I allocate this range of memory as based off of the size of how large this thing needs to be. I in-place construct it into that memory. And then I do this thing where I exhaust the pool. So I create and allocate from every single thing from the pool, and I unmap its guard page. And then I push back. So I record the pointer that I get. And then after that's all done, I go through all those pointers and I release them back to the pool. And then I free the contiguous range. I free that range of physical memory that I use for this purpose. And this seems to work. So that's what we're seeing here. Unmapping guard page for task stack at blah, 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 blah. Releasing task stack back to the pool. So at low numbers of tasks, this thing seems to work. What's up, NSG? Nice to see you. Thanks for popping in. So at low numbers of tasks, this strategy seems to work of like unmapping all their guard pages all up front. And then what I was observing is that this thing falls apart if I crank up the number. So instead of four tasks, it is 4,000 tasks. And this probably has some implications. Some implications that I might not be thinking about, but yeah, that was the idea. And so here's what happens if I try to run the kernel. So it is boot looping. It very much seems to be boot looping. So yeah, so that's the behavior. So there's something going wrong, and I'm not totally sure why. What's up, Ray? Yo, nice to see you. Yeah. My Kimu window is going crazy. I can't even drag it over because it's resizing itself like crazy. So, that's wild. What's up, Vitriol Cutie on the Twitch chat? Streams sound interesting. Love the work. Where are you currently at? Are you trying to figure out a good way to keep track of the guard pages committed to a process's address space? A little bit. I'm trying to figure out a good way to make sure all of the guard pages get unmapped from the address space when the kernel boots up. What's up, Abhishek? What's up, Bishmit? Any idea for... Yeah. Thank you for popping out that resources link digitalized. NSG. NSG with the wise wisdom as usual. When you're loading in a new task, it's better to flush the entire TLB. Yep, that makes sense. If you're unmapping, reflagging, just inval page it. Yeah. So NSG, you are talking about this comment or this comment. Right. Yeah, this is a bit of a implementation detail. I think, yeah, this is a little bit. I mean, I believe this is like orthogonal to what's going on right now with this thing. But yes, this is like inval page or reload TLB altogether. I think for context, the reason I was considering reloading the TLB is because I think it would be more, I thought it would be more efficient than doing inval page potentially like 4,000 times here. If I know, like basically just doing nothing in this big loop and then doing a single TLB reload seemed like it might be more efficient to me than doing like 4,000 inval pages. I don't know. I don't have amazing intuition about the performance of inval page compared to a total reload. So that's just what I'm talking about. But anyway, that's like a little bit of a detail. We're not even quite there yet because this thing is boot looping. So yeah. What's the best way to learn C++? That's a good question. I would say the best way is probably to write your own versions of some data structures, like a vector, write your own array, write your own unique pointer, write your own smart pointer, write your own string, stuff like this. Write your own lock guard, stuff like that. That's what I did. And just like, yeah, I think those are some good exercises. So how do we debug this? Let's just, I mean, the classic debug trick is to, let's just binary search this a little bit. Let's just, okay, 4,000 broke everything. What about 2,000? 2,000 also too big. I'm just gonna take a screenshot as usual to help me think through this. Trying to batch unmap the guard pages, boot loops. So, okay, let's just keep going. 1,000. Also, does it? 500. Also does it. Dang. 250. Also does it. Oh man. 125. I think this is just gonna something's crazy messed up. I'm gonna go with 65. Okay, 20-second break, be right back. Okay. So this is interesting. Okay, so here it made it a little bit farther. Interesting. Okay, this is kind of weird. But I think that's the boot loop. This is where it reboots. But it's weird that if we, what is it, how many is it? 30? Whoa. Page fault. Whoa, this is cool. So we're seeing what, this is at 15. What are we seeing here? So in this case, it actually finishes everything. It releases all of the stacks back to the pool, which should be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And it continues running the kernel and the kernel crashes later. An odd overflow memory issue, perchance. Maybe. Man, it would be really cool to get a stack trace. To be able to get a stack trace for this kind of thing. It's kind of annoying. Actually, wait a sec. Is it possible to get a stack trace? Because I'm in kernel mode right now, and there's no stack switching that happens on a exception, so I might be able to get a stack. Just attach GDB. All right. So actually, yeah. Because I'm just all the time in kernel mode, I do get a stack trace. That's kind of cool. And it's crashing in the first call. Ooh. To create task. Sorry about to sneeze. And it crashes in allocate. In the ETLI pool. Oh. Wow. Let's see. So what do we? I'm gonna keep binary bisecting. What about 7? At some point, it's gonna stop crashing, right? There we go. Stop crashing. So I can support 7 tasks, which is a big improvement from supporting 4 tasks. It's crazy. So yeah, like why did it page fault? What did the page fault say? So let's get back over here. Page fault on this address. I wonder. Oh, I think I know. Okay, this is interesting. I think I know. So the error code implies the page doesn't exist. Actually, that's a good call. What? How do I? Let me. What's up with the error code again? How do error codes work for this thing? I don't really even know if this is the right place. What number is interrupt? Page fault is 14. Yeah, how does this even work? Page fault exception. Okay. The error code has a format different from other exceptions. So obviously this thing is all zeros. Oh, so it tells you the reason for the page fault. Like, was it present or read write? Yeah, I have a suspicion for what was happening actually. So check out this address, and my suspicion comes from this address. This is a very interesting address. This is very close to the, so this is in the region of where the kernel is mapped. Look at this, vert base, yeah, vert base. So what do we know? We know this is an offset into the kernel itself, which is interesting. And yeah, and that this strongly points to the fact that I believe something is accessing the guard page. So we did all this, the last address. Yes, interesting. Sharp eye, yeah. NSG points out this address is the same as this address. So here's my suspicion, and here's the way I think this kind of works. So just to illustrate again, so we have this pool of stacks, and the idea is to go through all of these stacks in the pool and unmap the guard page and all the stacks such that for the rest of the execution of the kernel, we can assume that the guard pages are already unmapped. And to do this, what I'm doing is I'm like going through each of these things and I'm like allocating it, I'm unmapping the guard page, I'm holding a reference, I'm like exhausting the pool until I get to the very end and I'm holding all these references. And then what I do, I need to go back and release all of those references. And that's what we're seeing with all these releasing lines. And it's interesting that these numbers actually go up, which is sort of implying that it actually allocates from the back or something weirdly like that. I think that doesn't really matter. But what I'm taking away from this is that, so we had all these things referenced, we freed them all, and then at some point, someone else is going to come along and try to get a stack, and it's going to try to get one. And it's going to be the last thing that was released because I think it uses a free list internally. And so this is pointing at the fact that something is trying to write to the guard page. and it's faulting. We can very easily test this by commenting out one line of code. This line. If I no longer unmap the things, and the cause of the crash was trying to access the guard page, then there should be no more crash. I'm pretty sure this is the reason. So look at that, it didn't crash. So I'm pretty confident that something is trying to access the guard page. What's up, Kojit? Is there any repo for this OS? Let me hit you with the GitHub command. But it's not going to be what you want to hear. The answer is no. But the answer is there is a mailing list if you want to hear about updates for that. But for right now, it's a private project. If only there was a way to live share, but for the entire stream. What do you mean, NSG? Live share, but for the entire stream? What's RCX mean, Ray? RCX is a register. Not sure where you were seeing that, but it's a CPU register. There's RAX, there's RBX, there's RCX. So this proved that the problem is something is trying to access the guard page. Our stack trace shows that it's the code in allocate which is doing that, which is interesting. VS Live, you can have multiple people work in the same VS instance. Oh, okay. Cool. Your last memory address in one of the previous screenshots had R6 equal your address. Uh-huh. There, that's true. That's true. There's a sharp eye. Got some eagle eyes in the stream today. That basically just means that the code in ETL ipool allocate was using RCX at the time. That was probably the instruction that was like triggering the fault. It was like probably some kind of memory access using RCX actually. So basically the problem is something is reading from the guard page after it has been unmapped. That's what this is telling us, because we have all zeros, which means it's a non-present read in supervisor mode. Yeah. Hey man, I love your work. Always here on my feed. You've been doing this for 16 weeks. Has been an inspiration for me. I'll seem to be cracked someday. Keep going, man. Thank you very much, Kojit. You can definitely do it. You just gotta put in the work. But yeah, it's not magic. None of this is magic. It just takes some time to understand it. So, all right. So we know that it's a read. I mean, the thing that sort of gives it away is the fact that the present bit is 0, which means it's trying to access a page that isn't there, and it isn't there because we just unmapped it in the code. So it is very interesting that we are seeing this fault, because I don't believe I ever actually reloaded the TLB. And actually, I mean, you can see it right here. I have a comment saying maybe I should reload the TLB. I have a comment saying maybe I should inval page. I never actually do either of those. So for me, it's a little bit mysterious why this unmap actually did anything in practice, because the unmap doesn't do that. All it does is manipulate the page table entries to clear a bit. So that's not actually doing anything. So Vitriol Cutie, I probably didn't get it with spout bug guard pages don't get allocated so that an access triggers the page fault and you know the stack is corrupted. Exactly, yeah. And in my implementation of guard pages, I'm doing it in sort of a weird way. I actually explicitly have this stack structure that describes a guard page followed by a stack, which is ultimately getting like baked into like the kernel, like it's statically allocated in the kernel. And the entire kernel starts out all as mapped. And so in order to make the guard pages take effect, I need to go in and unmap them. And that's NSG. Wait, where is this even getting the memory from? Is this a global heap? And that's the thing. No, what you all need to remember, I don't do heaps. I don't do heaps, at least yet in my kernel. So everything is statically allocated into the kernel binary. And so to be clear, yeah, basically to trace it a little bit. So it's this pool of task stacks, which is part of, the scheduler class. The scheduler class is owned by the kernel, round robin scheduler. And there is a global kernel object. So no heap. We're all about statically allocating things. And so 20-second break, I guess. Be right back. Okay. I think it's really not. I think it's slowly becoming clear to me what's going on. Yo, Ismail in the chat. Nice to see you. We've been waiting for you. We got the gang in the chat today. Yeah, it's slowly starting to become more clear to me what's going on. Something is reading from the guard page somehow, and that is happening in response to a create task, which calls create. So create task, right? This is here where we're creating a task. This is code that's running after that init like phase where we go and unmap all the guard pages. So it's the first use of the pool after that point. And now we're getting into ETL's internals, which are like kind of, frankly, impossible to navigate. My IntelliSense does not even work. But what is this? That's crazy. ipool.h323. ipool.h323. So here we are. allocate item. Oh. Interesting. Does this get inlined? Why? Why did our stack trace not show allocate item? So create generic pool, create iPool, create allocate item. Which is a totally separate function. So it's not totally clear to me why. Did I miss something? Oh, wow. Wait, what? Okay, I'm not totally sure. This is like this, I don't know, the stub frame or something weird. But not totally sure why we're not seeing an allocate item. So this is a hint. 8080b6. Let's zoom back. Wait, sorry. No, yeah. Wait, how does this even work? What is this address even? Does anyone know? I think, is this the address of the instruction to return back to? I think it might be. Let's just do a quick sanity test with kmain. So what's this thing? 13cd. 13. Yes, is the instruction after it's returned to, basically. And so we're calling kernel run, and then this address is the thing after what is causing this function call. So going all the way up here, you know what? Is it possible to, and this is where I just don't know, Binja. Address, go to address. G, okay, got the G. Accept. Okay. But it's B6, which is not an instruction, question mark? What? It's close, it's an allocate item. But honestly, that's super weird. What about this one, the 3.5? Can we, does that work? Oops, G 3.5. Something is wrong. Something seems wrong. Something about the disassembly. It's either the disassembly or the backtrace. Something is not lining up. Like, these numbers are like a little bit imprecise. AD05 is not even valid code. So did I forget to compile? Maybe I forgot to compile again. Let me try that one more time. Okay, that was my bad. I forgot to rebuild somehow, and that was causing all these issues. So let's go back to this B6 thing. Right. Okay, so that makes, okay, that's starting to make more sense. Good. So here's where we are. The allocate item call is, so that, okay, for whatever reason, this is really calling into allocate item. But I think I know the problem though. Like, or actually, I mean, I'm still kind of confused because the way I'm declaring it, these things should be aligned on a page boundary. So maybe to help illustrate it a little bit more, what's really going on here is, so we have this pool and it has, like, let's say the pool has 4 things in it, and I don't know the exact layout, but internally inside, so this is a task stack, and the task stack is basically 2 things. The first half is the guard page, and the second half is the actual stack. But then there's also, like, I don't know, other metadata stored that is from ETL along with this thing, because it's like embedding my task stack into like a node or something like this. And there's like some metadata, and I think that's what we see over here. Maybe, you know, what we can just do, let's just like really debug it. Let's just try to step through to the place, create task. So it's in here. So task pool.create, right? So we need to step into here. And I'm just going to keep stepping until we get to here. Cool. So now we're, okay, scrolling is a bit weird. We are now in create, which is calling allocate. I'm gonna keep stepping more time. Now we are in allocate, and that's what we were seeing here. So we're in allocate. We're going to next, and now we're in allocate item. I'm going to step into here. And so now we are in the internals of this library. And this is, I'm not really like an expert in how this works, but it's this kind of pool allocator data structure. Internally, it uses some kind of free list, I think, for the pool. And let's just try to anticipate where we will get to. So any free space left? So there absolutely should be free space left. We can even print out some of the variables, I think. So repeat items allocated. Does this work? P max size. What am I doing? P max size 15. So that matches. initialize another one if necessary. So we did not do that. Interesting. What we can even do, this might be kind of interesting. We can look for RCX. So like Ray was saying, Ray noticed that RCX contained the address that was page faulting. Since we have the disassembly, we can just see where there are uses of RCX, and in particular memory dereferences of RCX. And these are offsets against RCX. Let's just this is this pointer actually, because RDI comes in, it gets stored into var10, which is loaded into RCX. But then I guess some other things overwrite RCX later. So let's just see what this thing, get the address of a new allocated item. Maybe it's this. What's up with this? What is up with it? It writes an invalid item pointer into this thing. Let's print a few things out. So there it is. That's our faulting address, and P next is a pointer to it. What actually is P next? It's a char star. So this thing allocates an item, then casts it to the pointer type. And returns it back. This is really hard to navigate. To create, which approximately was looking something like this. Yeah, create. And then create is where we take that pointer and then in place construct the object into that memory. And sort of a key part is that we like unmapped that memory from the address space. So let's just keep, so P next is a pointer to this faulting address. You know, it would even be pretty cool. I was trying to dump the page tables just to see. You can see the gap. I guess there's a gap here, right? You can see the gap between 40,000 and 41,000 is not mapped, which I think is the consequence of the unmapping. something I could add more prints about this. Actually, that might be interesting, but anyway, I think we're closer. So print next. So basically we can sort of read the code a little bit to understand. I think we're getting kind of close actually. Allocate item. So right. I think this is the problem right there. So we know that p next oh, what? We know that p next is pointing to this sort of like dangerously unallocated thing right now. And so any kind of access of dereference of p next is going to be dangerous. Or p-value, because p-value is also getting that. And so we can clearly see a couple danger points. So any dereference, so right here, that's looking pretty bad. It is casting this thing to a double pointer and then assigning p next. It's like something is up with this linked list. Something is like up with this linked list in kind of an interesting way. I've basically unmapped memory that is relied on by ETL, and as a consequence of that, I'm causing ETL to crash. And so there's one thing right here with this thing, and then this is also interesting. So what we can sort of see here is, even though these things are char stars, they actually, there's like some kind of pointer at the start of this object that they are manipulating. All right, 20 seconds, be right back. Okay, but I think, yeah, this is interesting. Ismail, I think this is not a bug in ETL. This, I mean, I'm doing something kind of weird. So to recap what I'm doing, I have this big pool of task stacks. ETL pool of like 15 task stacks or whatever. And a task stack is this struct that's like big. It's like 8,000 bytes, right? It's like one page for the guard page, one page for the stack. And I'm sort of assuming that this just stays because it's all statically allocated into memory. I'm expecting these addresses of all the guard pages are like kind of fixed and constant. And I thought it would be safe to just unmap. And because this thing is exactly one page, I thought it would be safe to just unmap this page cleanly. And as long as my code never accesses the guard page, I thought this would work, because I don't see any way that anything else would be accessing this page. But it seems like something is, and it seems like somehow the ETL free list or pointers or something are like in the guard page or something. like this. So what we can do to get more information about this is on map, we can print out some more stuff. So what I want to print out, so here's the big loop where we exhaust the pool. I allocate every single thing from the pool, and then I unmap, I get the guard page, and I unmap it. Maybe there's a bug in how I'm doing this. Does anyone spot a bug? But what I want to start doing is I want to print out some more information. So I'm going to print out I'm going to print out ptask stack, and we don't need this. Okay, I want to print out guard page. I want to print out guard page dot data, which should be the same thing. Right, saying it's not specified as a guard page, it's just a page, right? It's just 2 pages, and ETL thinks both are usable. But the thing is, ETL should not be touching this data. Like, this is my data in my struct. ETL should not be touching, even if ETL is managing a container that contains a bunch of instances of like my struct. ETL is free to manage the metadata surrounding that, but ETL should not be like modifying my struct. Like, that's not what it should be doing. So I want to print out a bunch of things. I'm very interested to see what's the difference in these 3 things. ptask, guard page, and guard page dot data. So these 2 should be the same, I think. And also, I think these 2 should be the same, and it should be page aligned. So I don't know. Let's just see something. Ooh, okay, so this, okay, oops. I want to get a pointer to this. Oh, okay, cool. So let's check this out in 4K. So interestingly, that number changed. Not quite sure why that might be. And did I forget? Oh, and this is does this work? Cast to a void star. That is pretty much exactly what I was thinking. RSP or NSG. You were saying, how are you setting the stack, like the tasks stack, when you set up RSP? I will just quickly show you what that looks like. So create task is here, and the way that the task, we're allocating a new task, and the stack, if you're asking about how the stack pointer gets set, that's over here. And so when we construct so the task gets a pointer to a task stack. and we get a pointer to the task stack, and we set up the landing pad, and we assign RSP right here. So I don't think that's related to this, because the code that's causing a problem, like this task hasn't even started running when at the point where the code is like crashing. The code is crashing in a much earlier, in this much earlier part, like right here, when we're even trying to even allocate a stack for the task. And this is already super interesting to see. Let me, are 68 and 69 backwards? Let's double check. Where were you looking? 68 and 69? So this code is actually not doing anything. This code was just P guard page is not used. It's actually only used for this print. And so these two lines, like these like lines, don't really do anything. They could even be commented out. Or I guess technically not. This one actually is used later, but this thing could be commented out. All these are getting local variables. But let me just, so this is really interesting just to see. P task stack, guard page, and garbage data, they all point to the same thing. So maybe I know what the issue is. I think ETL is not meant to work the way I'm using. I think ETL is not meant to support this kind of thing, like where the object in the container has this very particular alignment consideration or like requirement. I think that's the problem, because it's getting confused now. Like it's like trying to write into the actual data here, and I mean, to really understand that, we would need to get into the serious implementation details of ETL, which is maybe a little bit hardcore to like actually do ourselves, but I think we've earned a little asking of the AI. So I'm having a problem where this task stack structure, which is stored into an ETL pool, is causing crashes and page faults after I unmap the guard pages from all of the task stacks in the pool. And I have a suspicion that the ETL pool is not designed to handle these kinds of structures that have this kind of alignment requirement on the internal members. So can you please read the ETL pool and ETLI pool headers to investigate this? I'm gonna go with the opus. I'm gonna go with the high effort. Gonna launch that off. So that's my suspicion. My suspicion is ETL doesn't support this kind of thing, which I wasn't really thinking about that, to be honest. I was not really thinking about that. Just looking at some critical stuff. And so that is a bit of a bummer if this is true. That means we can't use an ETL pool for this thing. And yeah, I don't know, we might need something else, or not quite sure. What's ETL? ETL stands for Embedded Template Library. It is a it's sort of like a C++ standard library that's meant for embedded and freestanding environments, and it has a lot of useful data structures. And I had this idea that it would be really cool to use this for operating system programming. And I'm testing that theory, and I'm running into a bunch of issues. I'm getting like good things out of it, but I am also running into problems due to using it, which is sort of just how things go when you use third-party libraries. What's up, VA80? Busy day. No, thanks for joining anyway. It's going all right. It's going all right. Yeah, just kind of a bunch of debugging today. And yeah, and seeing that I thought I was being very clever with this task stack thing, and yeah, maybe not. All right, heading out. All right, cool. Thanks for popping in. I'll catch you later. Okay, here it found the spot. This issue extends when. Okay. ETL pool's free list mechanism stores a pointer at the beginning of each slot, and this beginning corresponds to the guard page member. What the hell? Once those guard pages are unmapped, okay, this is apparently pretty involved because the AI is thinking quite a lot about it. But what's up, Sanjay? Do you vibe code? Not really. Not really. Sometimes, but not for this OS project, really. The alignment is handled correctly by the ETL pool. Your hypothesis is likely wrong. The pool does respect the alignment. The real problem is the free list mechanism. ETL pool stores its free list char pointers at byte offset 0 of each slot. How does that make any sense? What's up? What's up, Apno Benzene? Hello. So this looks right. That's funny. Let me just ask another follow-up question. How could the ETL pool possibly store a pointer at the beginning of the stored user object type? Wouldn't that overwrite the user data? How is that possibly safe? Oh, it's safe because the pool only writes pointers there when the slot is not allocated. That's why. Interesting. Okay, that explains pretty much everything. So back over to this example. So I see. So basically there's all these slots and I'm storing task stacks, pretend it's like matching the whole thing. And half of this thing, the first half is the guard page. Second half is the real stack. I'm unmapping the first half. Because that's how guard pages work. The problem is that when a pool entry is not used, ETL sort of superimposes its own metadata struct. Like, let's say the pool looks like this. I mean, this thing. I mean, okay, it's hard to get that to line up. All right, let's just go down here. So let's say these are the pool entries. So this is how it looks. So these are unused ones, and in this ETL metadata for empty slots, which has like linked list pointers, and that's how it manages the pool. The pool internally has a free list, and it looks like this. And when you actually get something out of the pool, sure, it just gives you your whole thing. But then for the things that it's not using, it's mutating and actually using this initial empty space. So that's the reason for the crash, because I was just unmapping this thing straight up and leaving it unmapped, and therefore this first half is still going to be unmapped. Indefinitely into the future, but then ETL is going to try to use it, and that's what's causing the crash. I know it's very detailed. I hope anyone can understand anything at all that I'm saying right now, but that is the problem. So that's a problem with this specific approach that I'm using right now, where I try to upfront unmap all of these things on boot time and then leave them unmapped for the rest of the time. So that's not the absolute end of the road, though. There are some ideas, and so idea unmap all on init, leave them unmapped for the future. This is broken. ETL puts metadata at the start of the objects for the empty objects to maintain the free list. If that memory is unmapped, this crashes. So that particular idea doesn't work. What's kind of interesting is these suggestions it got. This is also such a funny suggestion. Does anyone see why? This is a very funny suggestion. This is a funny suggestion because it's first of all, it's wrong. It's completely wrong. It completely defeats the purpose of the guard page. The guard page must be below the stack in memory, because the whole point is to catch it when the stack pointer goes too far down and then goes into the guard page. It's saying we swap the order of these things, which totally defeats the entire purpose. Defeats the entire purpose. The guard page must be lower than the stack in memory. Yeah, trying to prevent stack overflows, meaning when you like do too many function calls and you go out of this the bottom boundary of the stack memory. I didn't get it. Why must it be lower? Okay, let me to kill the palm tree. Visually, it's easier to explain. So here's memory. Here is our stack, a task stack, and here's our stack pointer. And this thing is going to be going when we make function calls, when we allocate local variables. This thing goes down. It starts out at the top, and then as we make more function calls and stuff, this thing goes down. And the stack has a finite amount of space. It ends over here, and so it's problematic. It's bad if you make too many function calls and then overflow past the end of the stack and start like writing into random memory over here. And so the solution is you add a guard page, which is an explicitly unmapped area of memory below the real stack, which forces a crash page fault if this ever happens where we cross over the boundary. So this thing needs to be below, and that's what this struct ordering specifies. That's a really, really big stack pointer. You got it preventing overflow. Exactly. Yes. Got the big stack pointer. Yes. Okay, so also what's up Guvin, aka Passat. So it has some suggestions. Don't pool task stack directly. Isaki, why not something equivalent to an if statement, like if limit reached, throw some error? Oh, so you're talking about this thing. Because I guess there's just different reasons. Like one major reason is that you would need to be injecting that check all over the place. It would really slow down your code to be checking this thing all the time. And so it's like higher performance. It's not even in terms of like high performance, it's to even get any amount of reasonable performance, it's just not an option to be injecting these checks everywhere. So the way you do it instead is just allow this thing to go and then catch it with a fault in case it ever goes too far. And this should never happen, basically, for the record. It's a bug. It's like a bad bug in your kernel if you're overflowing into the guard page. So what's up, hello code? Nice to see you. Also, what's up, Leaf Erickson? I've got some explorers in the chat today. What's up, Dev? So yeah, so we got some suggestions. Don't pool task stack directly. Allocate each task stack individually with page aligned allocation. So you have full control. Pool a lightweight handle or pointer to the stack instead. Pool only metadata, not the stack memory. Have your task struct hold a pointer to separately allocated stack memory rather than embedding the task stack in line in a pooled object. Don't unmap guard pages from pooled stacks. Instead, keep them mapped, but mark them non-present in the page tables only when a task is active and scheduled. Remap on. So actually, I mean, there's some options. Pretty much 3, I think, is actually, well, yeah. These are some different options for solving the problem. I think 3 is like kind of simplest. And so what that looks like actually is, I think we can prototype that pretty easily. I also need to get going soon. What that looks like is, so all that code that I wrote here goes away. Particularly this line. And so, but imagine like this whole function, or maybe I'll just comment it out. Like I'm just like that. This whole thing just doesn't happen. What happens is this thing happens. So we're back to unmapping it when the task gets allocated. And what we need to do is sort of like remap it when the task gets destroyed, which is kind of weird. I don't know, if we could have a destructor that sort of does this. But then the question is, where does it get mapped to? So that's the idea. We would remap it back when a task exits. We would like remap the guard page such that the free list can continue to operate. But to do that, we would need to keep track of where to remap it to, which is kind of annoying. Like which physical address to remap it to. And so that would be something we would, I don't know, we would need to add some more state to the task or something to just to remember that thing. Which kind of sucks. It also, yeah, so it also would require another like inval page or something like this to happen here. So are you using a specific algorithm for scheduling? If yes, which one is your intuition to implement? I use a round robin scheduler. It's the most simple one and it works. And I don't currently have a reason to use anything more sophisticated. So yeah, I'm using a round robin scheduler. Looks like this: round robin policy, choose next task, iterates through all the tasks, and then chooses a runnable one. So it's pretty much as simple as it can get. Okay, so this is kind of a bummer. It's unfortunate that it gets so complicated. So what we could do is its advice is to like, like don't even pool it, just allocate a task stack and then Yeah, so there's some, yeah, other options are, yeah, don't pool. And so what number one sort of would look like is something like this, I think, where task. So what we would do instead, we would do mframe allocator dot allocate size of task stack by k page size, something like this. So we would allocate a range of physical memory, and we would then, so this would be like gone. Something like this, except it would be bizmap adder converter dot biz2vert. Like this, and then we have constructed a task stack. No, but then, no, this doesn't work because this is what I was doing even earlier, but the problem is that this is then in the phys map, and the whole point of doing this was to not have our stack be in the phys map. So this doesn't work. So that sort of leaves us, because this doesn't work, because I've been trying to really avoid writing a general purpose kernel heap. And I have just been trying to not do that as much as possible. So yeah, this doesn't work because it uses the phys map, which is not something I want to be. I don't want to have my stack pointers in the phys map because that's like kind of unsafe. And so the better way to the way to do this, if I were to do this approach, would be to allocate some virtual memory that can back this mapping region, which is not in the phys map. But that's exactly the kernel heap that I'm trying to avoid. So that sort of leaves us with the last option of pooling metadata, but not the stack memory. And I don't totally know how that would work. I wonder if there's some kind of trick I can use. So one thing that would work, I mean, this is like bad. I could also just do this metadata page. Right. Even ETL metadata page. This would solve the problems. Because then we still get a nice guard page that catches the stack issues, and we also have like a nice region over here for the ETL metadata. I mean, I'll just do it like this. Would almost certainly work, I think. But it that's interesting. That even still page faulted. On 5200, which is the guard page. So that's really surprising to me, because I would have thought that if we just leave a bunch of like writable data at the start of the struct, then ETL would be able to use that just fine. But something. Create, okay. That didn't work for some other reason, so. Yeah. So this is tricky. I think I had this cool idea. I think what I'm learning from this is I had my cool idea to use these pools for the stack and continue with my vision of like statically allocating things in more of like the embedded style. And it falls apart a little bit if I want to have guard pages. Guard pages and pool and this pool thing are not really matching very well. So I'm wondering what I could do about that. Yeah. Yeah, not super sure. I could not have guard pages. That I could just not have guard pages. That's not really an option. This suggestion, I mean, this suggestion number 1 basically requires writing some kind of kernel heap that allocates from virtual space. And maybe it's possible to write a very simple and constrained allocator for this purpose. Like a simple custom allocator. Which is not like a full-blown like kernel heap that allows arbitrary size allocations. So that's kind of an idea. This suggestion, it's sort of like adding a layer of indirection, and so instead of having like a pool of task stacks directly, it would be like a pool of task stack pointer type or something like this. But then there's still the fundamental problem of where to allocate the task stacks. So yeah. All right, I think that's gonna be pretty much it for today. Not the most satisfying end, but we thoroughly investigated this idea and are seeing some of the concrete pitfalls of doing guard pages. Like, it's a combination of like a couple things. It's like doing guard pages, unmapping them all up front, and then storing them in the ETL pool. And that combination of things is not really compatible with each other. So yeah, I wonder what other OSFers use for these as far as data structures go. So So the reason I'm running into this thing is I'm doing a different approach than like most other OS devers. Pretty much the generic like OS dever thing to do is just to immediately just go in on like a kernel heap, like kernel, malloc, and kernel free. And then just every part of the kernel just starts like using this like global allocator, which is a very natural thing to do if you just are in the mindset of like malloc and free. And I'm like pretty explicitly trying to avoid that school of design for a couple reasons. Like, I mean, for one thing, like that's just kind of boring to me. Like that generic school of just malloc and free is not really interesting. And I think people are not aware that there's other schools of thought around how to manage your memory, like specifically doing more static, fixed size allocations. And so for one thing, it's just kind of boring to me to use the typical malloc and free approach, but that would in some kind of way solve this problem, I think. The other reason is actually, I mean, people, like in a certain way, this malloc free software design is kind of a sloppy way to do it, because it's a little bit lazy. Like, you just don't really think, when you're programming, you just don't really think you don't intentionally really design the memory allocation behavior of your application, and you just like malloc and free and whatever, and then you just can't reason really very well about the runtime behavior of your program exactly. And that's the point of more of the static school of thought, is that it's like a different world, and then also you get some benefits from it. So yeah. The third reason is that kernel heaps are kind of hard to do. And I just don't, yeah. I've like implemented a heap before. Like I've implemented like a bad heap before. Where's my... Like, I don't know, it was like 11 years ago. I've like done that before. It's not super fun. You have like these chunk headers, like a previous and a next, and it's like this linked list thing. And maybe you have some macros, and you like search through the linked lists and like do all that kind of stuff. And it's like kind of tricky. You like coalesce the regions, and having a dynamic heap is a great way to like have security issues. And I even wrote some exploits against my heap allocator. You can overwrite chunks and like stuff like this. So I don't know, I've been there, it's like sort of done that. I'm like not so interested in it. So yeah, writing a heap is not fun. I ended up using TLSF because I got tired of debugging the one in my private project. You know, it's really easy to write a bad heap. It's really easy to write like a buggy, broken as hell heap that you just spend like debugging all the time. You know, especially when it comes to when you start doing multi-core and parallelism and stuff. So I don't know. I mean, yeah, I'm trying to avoid the heap, or team no heap as long as possible here. Implementing arc next. Crazy stuff. Atomic reference count. Okay, cannot click that. It's also slow. Sorry, I was missing some questions. I'm a fresher. I want to work on these little domains. I'm trying to study theoretical stuff from books. I want to do practical work, but I'm so confused where to begin. Yeah, I feel you, man. You need to take it step by step. But But yeah, my recommendation is always just to follow coursework. But yeah, honestly, you can also just DM me, to be honest, and I can try to give you some more support in on Discord, if you want to DM me. Coin. What's up, David? Ghosting your content for a while, thinking about starting. How to start a project like yours. MIT 6.828 or Harvard CS 61. I'll repeat that until someone actually does it. Okay. Cool. Nice. All right, y'all. That's gonna be it for me. So like I was just saying, I'm actually gonna be traveling for a couple weeks, and so here's the map. Here we are today, 116. The next 3 weeks are pre-recorded streams, and they are a bunch of stuff I was doing off stream that actually leads up to what I was doing today, and so a bit of like a Star Wars situation. And so the next 3 weeks are these pre-recorded things. I'll try to join in the chat if I can, but then I'll be back live on week 120. So, yep, that's pretty much it, y'all. Team static allocation. Get a better field than better. Absolutely, yes. This is the key benefit. Yep. Better than GC. Word. Us. All right, sick. I hope you have a great weekend, a great week, great next couple weeks, and I'll catch you on the flip side. Peace.